This is the sort of the political map with the main wards delineated here, and this is the groundwater quality map here. These two normally are not talking to each other, right. So, what I want to do in the next 30 minutes or so is to see if these two pictures are actually related to each other and how might they be related to each other. All right. So, I am going to use a particular framework, look at Bangalore as a living organism, and in particular I am interested in the metabolic process that keeps this living organism alive, right. So, from preschool let us get to second grade now. Living things breathe, living things need food, living things excrete. All of these things are true of any city, certainly of Bangalore. Living things grow usually only for a part of their lives. This is also true with most cities. If you look at history and if you took a slightly longitudinal view of how cities have grown, this is true too. Living things die, lots of cities die. Okay, so what is the problem? We understand a lot about what happens within the city, right. So, we understand a lot about Bangalore's circulatory system, if you will, right, and especially flow of rupee, certainly dollar. Circulatory system is what a social scientist like me is usually interested in, right. When we are interested in what businesses, people, etc. are doing within the city, but for this evening what I want to do is focus on the digestive system, right. I mean, I'm again using city as a living organism metaphor, and in particular I want to understand the connections between the circulatory system and the digestive system, right. I mean, how are these two systems related to each other, right. Okay, just to give you a sense that metabolic flows are crucial to keeping any city running. Food results in waste, energy results in waste, air pollution is really waste. Water, the public utility is for a reason called Bangalore Water Supply and Sewerage Board, right. I mean, sewerage is part of the metabolic flow. I mean, indeed at some point in my talk I will make the case that we fundamentally have a sewerage problem rather than a water problem, right. I mean, these two things are related, but if you wanted me to pick one, the sewerage problem might be even more serious, right. So, metabolic flows, as I said, share a two-way relationship with the circulatory system. There are three different ways to characterize this metabolism, and that is what I will do. We can ask the question, how are these different metabolic flows, in our case water, distributed between different people in the city, right. And I am going to be very specific here on questions of equity. I am going to abstract away from probably the most burning question in some ways literally, right. So, I am going to abstract away from how is river water shared between Karnataka and Tamil Nadu. I am even going to abstract away from how is water shared even inside Karnataka, right. When between agrarian use, between industrial use and between urban users, or even between different urban centers, right. I mean, that number 1400 million liters a day that I put up is not from thin air. BWSSB, the public water utility in the city, imports 1400 million liters a day of water because that is the maximum allowed by the tribunal, the Kaveri tribunal, right. But that is not what has been allocated to Bangalore, but that is what has been allocated to all urban users in the Kaveri basin, Karnataka part of the Kaveri basin, right. So, in some ways Bangalore has already appropriated what was really meant for different urban centers in Bangalore. Right, so these are questions that I'm going to completely abstract away from. I mean, I'm happy to come back and discuss, but I mean, you probably your sense on this is as good as mine. Right, so what I will instead focus on is distribution of water between different people in Bangalore. Right, so distribution entirely within the city. I'll ask the question, what volume of flow is actually sustainable from a biophysical sense, right? And how are these flows distributed between different activities in the city, right? I mean, that ultimately really is the economic efficiency question, and we will look at the intersections between social justice, biophysical sustainability, and economic efficiency, right? So, to get started, Bangalore as a living organism is sick on and unhealthy on all three counts, right. So, I'll present some data. I mean, much of this work is also based on a very large household water survey that we conducted in 2013 and 2015-16, but I'll keep that aside. I mean, and if people really wanted to see numbers, I can I'll bore you with numbers. But the basic point is political economy of distribution is fraught with inequities on multiple dimensions, right? And I can give you some very simple examples, right? I mean, you don't have to look at inequities between people that have access to surface water supplied by the public utility and people that don't have, people that live in nice neighborhoods versus people that live in slums, so on and so forth. But even if you took only those households, right, I mean, that already have access to metered surface water, Kaveri water from the public utility, there is a huge inequity even there, right. I mean, some of it is driven by extant infrastructure, right. I mean, for example, and this is probably of interest to folks here at IIHS, as most of you know, the modal dwelling type in our city is a multiple dwelling unit, right. So you have 5, 6 families living in a single building. I mean, that's the modal dwelling type in the city. For very practical reasons, water supply is supplied to a building rather than to a household, right. So what that means is people living in households in a multi-dwelling unit are actually paying lot more for water than somebody that's living in a single family home in a similarly sized plot, because of there's a block tariff, so that you hit 20 people in a building obviously are consuming more water than 4 people in a building, right. So there are many layers of this inequity, right, and then we will look at some of those as we go along. I mean, I think we'd not be meeting here this evening if most metabolic flows are not physically sustainable. Certainly water isn't, right, and flows are not economically efficient either. That's again a case that I really do not need to make. All right, very quickly, this is probably superfluous for an audience like this, but fundamentally, and Krishna is here, so I hesitate to do this, but this metabolism problem is fundamentally a spatial problem, right. So you need to understand the spatial variation in these metabolic processes. So this is roughly how the city has grown. The way I usually try and make sense of this is 2011 Bangalore is roughly speaking 2001 Bangalore plus 2003 Chennai, right. So I mean that's the clip at which Bangalore has grown, but more importantly is to ask the question of spatial distribution of this growth. So what this shows you is the growth rates between 2001 census and 2011 census. Much of the growth is actually concentrated, and nearly all of the growth is concentrated in the periphery of the city. For those of you who are from Bangalore, I want to underscore the fact that the numbers here are normalized for the post 2007 frame, right? I mean, so this is when we talk about, say, growth in this particular ward, for example, this was not even in Bangalore in 2001. So what these numbers are telling us is, we asked the question, how many people lived here in 2001? We know how many people lived here in 2011, and this is just the growth rate, right? So this is a common frame across 2001 and 2011 census. There are parts of center city that even experience negative population growth, right? So keep this picture in mind, because this is going to be the primary driver of a lot of the results that we will see as we go along, right? So the city looked something like this, again drawn to a common scale in 2001, and this is what the city currently looks, but the data is from 2011. Right. So most people living in the center of the city, most people now living in the periphery, right. So and obviously the next thing I'm going to do is juxtapose this picture with the distribution, spatial distribution of water supply infrastructure, and that is what is going to drive the social hydrology of the city, right. So I mean, just if you wanted more proof that Bangalore really has grown, this is from Nightlight's data, but this is important. What I want to emphasize, and this is already seen here, is that growth has been more or less uniform, right. I mean, there are obviously, so what I've done is looked at essentially growth in every direction, from the population 2001 population weighted centroid. I mean, I simply have looked at how the city has grown in different directions. Now you can obviously look at an airport effect, an electronic city effect, etc. But largely city has grown all around, right? Okay, and just to give you further evidence that city has really grown all around, this is the 2011 population centroid. This is the 2001 population centroid, right? I mean, and it's less, they're less than 300 meters away, right? So population weighted centroids from 2001 and 2011 very close together. So is the population growth centroid, and which is not very far away from the geographic centroid of Bangalore, right? So essentially what you've seen is growth around the city. In 2001 you didn't have any wards over 40,000 population, and now most wards are over 40,000 people. All right, so putting it all together, let's get to water supply, right? So just for those of you who have never seen Bangalore's water supply infrastructure, it should be familiar to a lot of you. Water comes from Kaveri, which is roughly 100 kilometers away and about half a kilometer below the Bangalore plateau, right? I mean, so we are actually pumping up, and we'll come to that. I'll end this talk with the water energy nexus that is very, very serious, right? When we look at the emissions from simply keeping the domestic supply of water going. Okay, so just to give you a sense of how we've gotten here, the top panel is aggregate supply measured in MLM, or million liters a month, and this one is LPCD, or liters per capita per day. So what we have is 2008 to 2014. basically what the city has done historically is every decade it's added a new pipeline to the river, right. So, I mean that's more or less the story. So, the dotted lines are historical numbers here, so that MLM has continuously increased with each addition. This last increase that you see is from the final Kaveri phase that was completed in 2013, right. However, in terms of per capita, actual per capita availability of this surface water, we are currently just about at the level of 1980. Right. So, after the latest addition, we have gone back to 1980s level, right. So, all that in per capita availability terms, what the latest round of infrastructure addition into 2013 did was to take us back to the 1980s level, right. Okay, this is the older. I'll also present the these administrative maps of the public utility keep changing, and it's interesting why those things change. When those things change because they need to promote an assistant executive engineer, and an executive engineer needs a division of his own usually. All right, so this is domestic consumption in liters per capita per day. What I want you to focus on are not these numbers, right. I mean, let's focus on the center part of the city, right. I mean, one that is served by old piped water infrastructure. Even here, right, the river water accounts for on an average only 72 to 90 liters per capita per day. Right, and by all accounts, the average consumption is roughly around 140 LPCD. Right, I mean, and that's the number we get from our survey, but I mean from many other sources as well. I mean, and I'll use for the lot of the thought experiments that I will present, I will use 150 LPCD. The consumption is anywhere between 135, 155 on an average across the city. The main point here though is there is not a single part of Bangalore that relies entirely on Kaveri water, right. So, every single neighborhood, right. I mean, obviously I can actually give you numbers on it. I mean, there are several hundreds of thousands of people that rely entirely on piped water from the public utility, but there is not a single ward, if you will, certainly, and certainly subdivision where the entire locality is dependent only on surface water, right. So, we are in a mixed surface water groundwater regime, certainly in the periphery, right, because I mean there are places where you have only 3 liters to 20 liters per capita per day, when as you will see there simply isn't piping infrastructure there. So, this is the current subdivision, right. So, one of the things that happens in 2013-14 is BWSSB actually changes its jurisdiction, so that these real peripheral areas are even to begin with outside its purview, right. So, they are not going to be ever covered with piped water supply, but there is also a little electronic city that is now part of BWSSB. We can talk about that later. All right, so this is the piping infrastructure as it exists today. So, the dark blue that you see is the last phase that was added in 2013, right. So, 2013 basically added the dark blue, and the older ones are shown in the lighter shade here. All right, and this is directly from BWSSB metering data. So what we did was essentially got hold of every single meter volumetric data between 2013 and 2015 and averaged it out. This is again consistent with what you see here, right? So even by their data, when there are pockets that do, if you do it at the ward level, there are probably pockets that are completely dependent only on BWSSB water, but they are far and few in between. All right, and this is the Borewell dependence. If you looked at census 2011 data, once again this is clear, right? So people in the periphery are essentially dependent on borewells. Okay. Just to put this all a little more starkly, what I have done here is plotted average surface water LPCD. This is what is actually consumed, right? I mean, after all the transmission, distribution losses, which we will come to, right? I mean, given the current crisis, there is a lot of talk on distribution losses, transmission losses, etc. But we want to step back and look at if these losses are actually as serious as they are made out to be sometimes. All right. In any case, what you see here, these are individual BWSSB administrative subdivisions, the map that you saw just a little while ago, and this is the population of those subdivisions, right? I mean, which have essentially obtained by using ward population and intersecting it with larger subdivisions and then subtracting away most obvious features. I mean, I'm happy to go over how these population numbers came about, but fairly standard ways of doing it. So there's a clear negative relationship, right? So the most populated parts of the town are also the most underserved by BWSSB. Right? And if you did the same graph with x-axis now population growth instead of 2011 population, the negative relationship is even more stuck, right? Okay. So now you want to ask the question, what are the consequences for the interaction between surface water and groundwater based on what we have seen, right? I mean, this mismatch between where people live and where cities' water infrastructure is located. All right. So I mean, this is again just to give you a sense of how the pipeline developed. This is the current water infrastructure. This is electronic city. All right. Okay. Now I want to put all the Bangalore maps that you have seen on top of this system, right? I mean, so this is Bangalore without the city, right? I mean, if you could wave your magic wand and simply make all the 10 million people, 10 million plus people disappear, this is what you'd be left with, right? So, and then we'll do a thought experiment on what the 10 million people in Bangalore combined do to background hydrological processes, right? So, we are going to now put back Bangalore on here. Okay, so let's try and do basic water balance, right? I mean, Manish is here. I mean, I know Krishna has worked on this. There is huge disagreement. I mean, of the 14 people on the byline here for this talk, there is complete disagreement, right? I mean, I do not agree with many of my co-authors on exactly what the water balance of the city is, and this is after 3, 4, 5 years of 3 or 4 independent large-scale projects trying to get at this. We will look at the reasons for why urban hydrology is hard, right? I mean hydrology, when we talk hydrology, the first sort of image that comes to anybody's mind is pristine forest, stream flows, you're camping on a riverside somewhere inside a national park, perhaps, and measuring streams, etc. That's easier than trying to do this in an urban setting, right? So there are lots of uncertainties that we will talk about. Okay, so this is a thought experiment. So I'm going to start off by looking at Bangalore as one single entity, right? So we are going to look at the water balance, assuming Bangalore is just one big tank or bucket or whatever else you want to imagine Bangalore to be. All right, so there is rainfall. There are no people, right? I mean, so I hate doing this as an ecological economist, but anyway, I'll use the term natural state, quote unquote natural state, where there are no people. So you have rainfall. We'll assume 80% of it evaporates. I think a fair assumption. 10% stream flow, 10% rainfall recharge, so that the net groundwater discharge is about 10%. Right. So in absence of people in the city, this is what would be happening. Right. Now let's bring in the people. Right. So first off, there is rainfall and there is external water supply. Right. Remember, this arrow is 1700 million liters a day and this is 1400 million liters a day. I mean, that's the reason why these two are drawn to be nearly of the same magnitude here. And there is evaporation, of course, like before. There is stream flow, but percolation is hard, right? I mean, we really have no clue. Right? I mean, even after working on this for 4.5 years plus with some of the best hydrologists who have looked at Bangalore, I don't think we fully understand exactly what the artificial, quote unquote, artificial recharge is. So I am going to make some assumptions. These are useful guesstimates. All right. So and we have no idea of what is being pumped out either, right? And I will go through ongoing efforts to actually estimate the total amount of groundwater withdrawal in Bangalore. Number of different strategies that we are adapting to come up with a reasonable number for this. So we don't really, the idea is there are lots of uncertainties, but anyways we will start putting numbers, right? So consider the quote unquote natural state, right, without people, and I'm going to convert all of these things into millimeter per year. So rainfall recharge is 63 millimeters per year. If you netted out all of the things that you see here, you get a net recharge of 63 mm per year. So that's your baseline case. Now consider natural recharge with leakage. Right? I mean, after all, you're bringing in 1400 mld of water. Some of it leaks and it finds its way into the groundwater system. Right, and this is a good place to pause and think through leakages, right? Because I mean, leakage has been in the news a lot lately for all the right reasons. You do not want to look at water infrastructure leakages through the same lens as, say, you would do with electricity leakages. Right, because we were looking at two very different entities, and it's common for media reports, for example, to juxtapose one with the other. To give you some benchmarks, right? So estimate, and these are again guesstimates, right? I mean, so we don't really quite know what the overall leakage is. but guesstimates suggest that we are within 10% of other major Asian cities with comparable water infrastructure. Right? I mean, for example, people on this project group have compared Bangalore with places like Bangkok, Seoul, Tokyo, etc. Leakages are comparable. I mean, when these leakages are part and parcel of running this large infrastructure. Right? I mean, after all, you're trying to transmit and distribute 1400 million liters a day, which is essentially creating a rainfall system of your own. Right? So keep that in mind. So if we assumed a 30% pipe supply leakage, I'm happy to debate where this 30% number comes from. Manish is also here. We can do that in the Q&A. So that alone is 140 millimeters a year. Right. So what you're already seeing is the groundwater recharge from leakage is already greater than the background recharge. Right. But there's also pumping. So we and I'll come to some numbers on pumping, but at the moment let's simply assume, and then we'll look only at the domestic sector. Right. So we will set aside commercial, institution, industrial uses of groundwater for a little while. Even in the domestic sector, we'll assume that if you don't get 150 LPCD from the public utility, you are going to drill a well and get the balance out from groundwater. Right. So that's the assumption, which leads to a 360 that translates to an equivalent of 360 millimeters a year. If you net everything out, your water table is going down by 157 millimeter a year, which we know is not quite right. Right. So there's obviously something missing. Now you want to include not just natural background process and water supply system leakage, but also the return flow. Right. So if you included return flow, I mean, after all, after you've used the water, it has to find its way back somewhere. Right. And I mean, just before we started, Manish and I were talking about just how little we know where exactly return flows happen. But nonetheless, in this simple lumped model where there's only one bucket that you're interested in, that accounts for about, again, 138, because not surprisingly this number is the same as piped water leakage, because whatever you use is returned. And if you now net everything out, you're left with about 19 millimeter per year is what you have. All right. And is this realistic? This is, after all, only a thought experiment where we said domestic usage is 150 LPCD. If we make a further assumption, and I'll present evidence for why that's reasonable, probably a reasonable assumption to make, that domestic sector groundwater usage accounts for about 45 to 50% of the total groundwater withdrawal in the city. You can begin to build a distributed groundwater model, and going away from this lumped model, and stuff that Manish and my colleagues Vishal and Shekhar do. Right. So this is the possible change in groundwater with the assumptions here and the assumptions about commercial industrial use. We've to try and locate the commercial industrial activity in the city, what we have largely done is used the electricity utility data. Right. So we've used BESCOM data to try and figure out where the commercial entities are located within the city. right? I mean, because and we, like with BWSSB, we got the entire billing data from the electricity utility, so that we know where are the hotels, where are the I mean, I'll come to marriage halls, because that occupies a special space here in our efforts to get the model to track back history. In large institutions, software parks, so on and so forth. I mean there are about 17 different categories of commercial connections that BESCOM has, and then we have some estimate of what a small hotel might consume. We have some estimate of what a large institution might consume, etc., and we simply multiplied by number of such institutions in any given part of the city. All right, so is this plausible? There is some evidence, right? So in the center part of the city, you actually do have some wells that have been monitored by mines and geology over a few years. Our collaborator Shaker at IIHS has also been monitoring some wells. Manish is very much part of that effort. So there is some corroboration that the water table is indeed rising in the center part of the city. This again is not very surprising. Right? This is common with many Asian cities. The best known example, of course, is Tokyo, Japan. Right? So if, anybody who's been to Tokyo knows so much of the city is actually underground. So in late 1960s, Tokyo, in order to protect its groundwater resources, essentially for all practical purposes stopped any pumping at all within the city, right? And what that meant is water table kept rising, because Tokyo water infrastructure also leaks, like the Bangalore infrastructure does, and so that now they actually have to deploy pumps at strategic location to pump water out into the city. Just to maintain their underground infrastructure, right? And this first came. So some of these measurements were first done when Shaker worked with the metro construction effort, right? There's a part of Bangalore metro that goes underground. Okay, and this is where I want to once again go back to why looking at hydrology as social hydrology is fun, and certainly important. So while Vishal was trying to get his distributed model to sort of converge, he was having trouble, right? And there was one lumpy element that was clearly missing. Even from certainly from the commercial industrial part, it turns out that if we added back in all the water that is used by various marriage halls or the kalyan mantaps in the city, we were actually quite surprised. An average middle class wedding in the city can use up to 120 kiloliters of water over 2 days, right? And I think we've done this in multiple places, so that seems to be the number. So at least 70 to 100 is a good estimate of amount of water that can be used at weddings. And you put that in the peak wedding season in India, and then things started to actually converge. So just to give you a sense of why this is much harder than doing traditional hydrology, right? But some of it is also water quality, right? This is a water quality map. This is not from our work. This is all the red ones are non-potable, yellow ones are probably okay, blue ones are the only aquifers that remain potable, right? I mean, part of this is obviously driven by the fact that you are now, I mean, there's obviously an industrial effluent story, all of that, but also the fact that groundwater depths are changing, and you're now drilling beyond shallow aquifers that you see. There's more evidence to show. So, I mean, there are these are 3 wells. I've just picked 3 examples here. Wells monitored over a long period of time by Department of Mines and Geology, just to give you the sense that there is an irrefutable anthropocentric signal in water table depth. So, both this is Baidarahalli, this is the well that you see. What's happening here is rapid expansion in city population in that part of the city, and no access to piped water. So, obviously, water table depths are falling. In the center of the city, which is here, the bottom panel, this place has actually experienced negative population growth and well served by the public utility. So, you actually seen increases in water table here, and yeah. Okay, the years are, so this goes all the way from 1990 actually. So I mean, I've just picked 3 wells where we have long term data, and there is this on the eastern fringe where you don't quite see social hydrology working, right? I mean, because things different factors are balanced out. I mean, it's partly served by the public utility and has experienced only modest population growth, so on and so forth. Okay, my favorite social hydrology story though is not from my own work, but a really interesting project led by my colleague Sriram, working with researchers from Duke University. They've been interested in looking at social mobility within slums in Bangalore, right? And I mean, I got interested in this because their map of social mobility sits really well with water utility map of the city, right? So, as part of a large water survey, one of the most fascinating things we discovered was Bangalore has not one utility, which of course we all know, Bangalore Water Supply and Sewerage Board, but at least 3,000 other utilities, right? I mean, these are basically neighborhood scale utilities, often run by the local corporator. So, essentially this is possible only in areas where groundwater levels are such that you can tap into it, initially even quote unquote steal electricity, get this going. So, the rough story and the sort of hydraulic hypothesis, if you will, for social mobility in the city, and Anirudh and Sriram are actually working on this to see if there is real evidence for the hydraulic hypothesis, is the following, right? So, you start as a squatter in the city, quite and this is not exactly random. So, I mean, if you happen to migrate from a certain taluk in Karnataka, then you begin life in the city in some place. If you happen to come from a part in Tamil Nadu, you begin elsewhere, so on and so forth. I mean, these are segregated spaces, to be sure, but your chances of social mobility is very intimately tied to simply where you begin your city life, right? And one of the factors, and at this point it's only hypothesis, but I think I have every reason to believe it will stand scrutiny, is simply the geographic location, and that has to do with access to groundwater, right? Because what the causal chain is as follows, right? I mean, so if you have water tables that are easy enough to tap into, your local corporator sets up a city scale, a neighborhood scale utility for you, often getting electricity into the neighborhood for the first time. Once electricity comes, the process of quote unquote regularization, formalization proceeds, right? So your life chances vastly improve. In a year and a half or so from now, I'll be able to come back and hopefully confirm this hypothesis. Sriram and Anirudh are working on it, but I mean, I think this does seem to be the case. All right. So a lot of what we did comes from a very large survey that we ran in 2013 and partly repeated in those houses with groundwater in 2015-16. We initially surveyed 30,000 households across the city and did a detailed survey in 1,500 households to get a sense of simply how people use water, right? I mean, and even with public supply of water, these are the different ways in which you can access publicly supplied water. I mean, there are more than 1% of Bangalore's population using up to 13, 14 different sources of water, right? So I mean, we are in a very, very complex water supply environment. But what I wanted to focus on now is the third part of my metabolism picture, right? And questions of economic efficiency. Right? I mean, one of the often cited story is one way to address our water conundrum is to simply price it right. Yes, I mean, sure. I mean, you want to price it right, and most of us pay only a fraction of what it costs to bring water into the city, so on and so forth. But there are innate constraints to how you might even do this. I mean, let me illustrate this by asking the question: can I come up with a system of water demand? Right? I mean, can I estimate water demand equation for the city of Bangalore, I mean, across all of these multiple sources of water? In basic 101 economics, even for those of you who are not economists in the room, to be able to estimate a demand curve, you need marginal cost. You need to know how much am I paying for the next liter of water that I am consuming. Right? And it turns out that this information across multiple sources of water is scarcely available. Right? So, for example, with BWSSB water piped into your dwelling, right? I mean, sort of, we are basically talking about at least lower middle class homes. Only about 20% of the households actually no marginal cost of water, and this is significant because any water conservation effort that relies on solely a price signal, right? I mean, so the assumption behind price water appropriately is that if you are paying at the marginal cost, then you are going to alter your behavior. But thanks to the fact that the modal dwelling type is a shared housing, that simply isn't true. So much of the storage infrastructure, so much of the piping infrastructure is all shared. Right? And there are several households that don't even know the average cost of water, let alone the marginal cost of water. Okay, so the other sort of ongoing effort really led by Manish is doing this with Shekhar and Vishal is to try and get a better handle on what exactly is happening to groundwater in the city, right? I mean, there are two key variables that we are interested in. One is, of course, the groundwater depth itself, and B, can we use this exercise to sort of triangulate our throughput estimate, which is the amount of groundwater that we are withdrawing as a city, right? So what Manish is done is to divide up the city into 28 cells, and in each cell you're sampling what, 7 or 8? Five wells month after month, and the idea is to build a simple 1D and again probably even a 2D model to try and come up with an estimate, the first sort of citywide estimate for what might be happening to groundwater levels, right? And this is a great picture. And this is a January picture, so this snapshot probably doesn't show you the entire story. The biggest evidence for social hydrology is what our team has been calling it the flip, right? I mean, absent people in the city, I mean, given the topology of the city, you would expect that groundwater levels in the periphery, right, are actually closer to the ground than in the center of the city, right? I mean, because I mean, remember we are actually IIHS is not very far from the highest point in the city, right? I mean, which is the high ground somewhere near high ground. Chalukya Hotel is the highest point in the city. So absent people, you would expect that groundwater levels in this part are at their lowest point, right? So and in the periphery you would have it closer to the ground, and you obviously observe the rivers. And one of the things we are trying to do is characterize this flip. All right. Okay, and this is Manish's team doing this month after month. I want to quickly end by, I mean, I want to keep enough time for questions, so I will skip over some of the details here, but illustrate the fact that there is a very important water energy nexus, right? I mean the energy costs of keeping Bangalore's water supply going are enormous. We use the exact same distributed model that you saw earlier to sort of estimate the per capita emissions in kilograms per year from simply domestic water consumption, right? And obviously the high numbers that you see here are because these are areas that are recently been covered by the Kaveri infrastructure. Most of these energy costs, given current groundwater depths, are from transporting water from 100 kilometers away rather than groundwater extraction itself. Right. I mean in some ways this is a useful exercise because at least from an energy perspective and from a number of other perspectives, I mean politically fraught as it might be, it's useful to ask the question, given that BWSSB is really a network, there's no reason why one part of the network should get water supply that's very different from other parts. I mean it's a question of allocating water across different parts of the network. I mean it's not as trivial as that, as some of you who studied the piping infrastructure will know, but it's not an insurmountable engineering problem. Right? And certainly relative to some of the Star Trek solutions that we've seen discussed in recent weeks and months. All right. So from a hydrology perspective and from energy cost perspective, you would want water to be disproportionately allocated to the periphery, because most people live there, and it's actually easier to access groundwater in parts of the city like where we are currently, because you can probably sink a well outside here and you will strike water at 20-30 feet. Right. So, unlike where I work in IIMB, I mean, I know there was a Borewell drilling that happened last year, and at 650 feet we gave up. Right. So, there's something to think about. All right, but this is not again a Bangalore specific problem. Right, and one way to characterize the energy water nexus, it's serious enough that you might benefit by thinking in terms of water return on water invested, right, when borrowing from the more familiar energy return on energy invested sort of accounting framework. So, what this means is it actually takes water to produce electricity. Right. I mean, for those of you who follow energy infrastructure in the country, the limiting factor today in many of the new thermal power stations is not coal but water. Right. So, I mean, when after all a thermal power plant is essentially a sophisticated water boiler. I mean, it really is a water boiler. Right. So, what we have done is calculated water return on water invested for various cities. So, what you get here is for every city except places like Mathura, Kanpur, etc. They are exceptions because they are in the Indo-Gangetic plains very close to the river. This is a problem throughout much of India. Right? When in Bangalore, for example, about 4% of the water that is brought into the city is essentially used up to simply keep the so we've actually used the mix of thermal hydel power that powers all this. About 4% of total water is simply used to keep the pumps running. Right. So, that gives you the sense of water return on water invested. So, let me conclude by so how then do we approach social hydrology? Right. And one of the ways in which our group has been doing is to concede that there is no reason to believe experts have all the answers. Right. I mean after all, we have at least 3 distinguished hydrologists on the team who have done this for a number of years, and we don't seem to actually have much of a handle on the problem. So, the idea is, I'll skip over this. I wear a business school hat, so I had to slip this in my lecture. This give you a sense that experts don't always know what's happening, right? So, this is a very famous example. In 50 years ago, scientists at RAND were asked to describe what a home computer might look like in 2004, right? And this was their vision of what they thought the computer would look like. But obviously, this is not where we ended up, right? So, so experts are useful when we are dealing with either high uncertainty or something that is very impactful. But so you can deal with variations, we can deal with trends, but when it comes to critical uncertainties, you have to look beyond normal planning. Right. So, that's one of the things that we've just started doing, which is to say, can we get everybody in the city participate in a scenario modeling sort of exercise. So, what that means is you conjure up what the city might look like, that that goes into, and then you can play around with some of the early toy models that are available at urbanmetabolism.asia, and then you feed it into a background model, and it spits out what the city might look like. If you don't like what you see, modify your assumptions. Right? It could be a number of things. Right? When things like what about reuse of water? I mean, it is clearly important. But one of the sad things I found from this large survey was well under 25% of households in Bangalore. Right? I mean, this is all weighted, everything. So, at most 1 in 4 households in Bangalore, at least in 2013, was willing to use recycled water for anything at all. Right? I mean, just in terms of attitude. So, what does that mean? I mean, these are scenarios that you can throw in here. Right? I mean, what about sewage treatment compliance, or can you actually comply with the laws the way they currently exist? Rainwater harvesting. I mean, all the usual sorts of things that get listed. You can throw in and see what difference it makes. All right. So, number of institutions to think through. I mean, this it's a multi-institution effort that was presented here. I will stop here. I'm happy. I mean, I have some numbers from the actual survey. So, if people are interested in nitty-gritty numbers, I will throw them at you.